This video is a quick introduction to VHDL, the hardware description language, used commonly for FPGAs. GHDL, free open source simulator for VHDL, and GTKWave, which is a signal viewer that's also open source. Quickly walk through how to install GHDL. We're going to build that from source. We are going to go through how to compile a VHDL program. We're going to go through how to simulate it and how to view the waves. And we'll also do a quick dive into the VHDL program, the RTL, just so you get a flavor for that. All right, so let's go to the code. So this is my GitHub account. You go to here, click this, Control C. I'm running on Ubuntu 22.04. I think they call it Jammy. And hit clone as it paste. It's good. Hit an enter. All right. CD GHDL examples. Here's CD examples. Here. And we'll take a look at source code in just a moment. Now, before we do that, let's kick off the compile for GTK waves. Oops, where'd it go? Where'd it go? All right, so let's close this out. So we'll go through. Now, one of the things is hand install directly with GHDL and GTKWave straight from an apt-get, update and install. A long time ago, and I think it might have been possibly when I was running off of Ubuntu 20.04, which I think was called Vocal. I think I got this error. And so in case that error does crop up ever again, I want to be able to build with the source files. So we'll go through these steps. Let's do a copy here. And again, this is my GitHub GHDL examples repo. You can see if this actually works here. Go to here. Let's paste. Okay, it looks like it might work. Hit enter. All right, there she goes. Looks good. Looks like it's now downloading the ADA compiler from gnat. That looks fine. And now it looks like it's actually compiling the ADA compiler from source code. All right, so while that runs, let's go take a quick look at the VHDL example. So similar to Python, you do a bunch of your library definitions at the beginning. Now, I might keep relating to this as Python. To me, I think that in Python, they went and they may have started with something similar to this language in their head, but they went and they cleaned it up a great deal. So I think that this ADA and VHDL, most likely ADA or Modular 2, provided some general background on what a language should look like, but Python took it above and beyond. So anyway, but we set up the libraries. Then we have this two-piece construction here. We have an entity which defines these generics, which are kind of, you can view as constants. So it's like count width is going to be always like 27, which means like 27 bits. Then you have a port list, which defines all the inputs and outputs. You can see the syntax of it. So you got a clock and and a reset, which are inputs. Defines also the type, which is standard logic, which is a single bit, similar to a Boolean, or really it's more similar to a character. Um, and then you can also have, in this case, and then you can also have down in, get to that in a second. So you have an entity which just defines the IOs. Then you might have different architectures for it. Some of the architectures you can write an architecture that's built for speed, built for simulation, built for just synthesis, made out of logic gates. You can have all sorts of different architectures. And so in this case, the name of this architecture that I called it is RTL. You could make it any name you want to. And it's a blinky, which is this entity. So that's how those are linked. Um, Almost always you only have one architecture for an entity. So I think this structure is really probably kind of overkill for vast majority of the uses, but it's not much of a pain because it's just basically you just create an architecture outline. Then you define the signals, which are kind of like variables. You define the signals. In this case, I define this. I have a commented out. Dash dash is a comment. This signal count, which is of standard logic vector. You can almost map that in your head to a fixed length string. And that's usually defined to define like a vector of many logic bits. And it's like really a vector of standard logic vector, uh, which you can view as a character, but is really a bit. And then we have this one. You can also have many strong. It's a very strongly typed language, and so you have a standard logic vector, which is just a jumble, which is a collection of bits. And then an unsigned means that like it's just goes from 0 up to n. You can have a sign which goes from minus, n to plus n. So it's a very strongly typed language. And then you have a process which essentially gets kicked off every time this clock signal comes in from the outside world. So when like your test bench or like your oscillator on your board toggles on, and whenever that toggles, this process gets executed and it waits for the next time the clock toggles. And the very first line is we check and say, oh, is it a rising edge? The toggles are going high or going low. Flip-flops in FPGAs operate on only one edge, not on both. So in this case, I've got a rising edge, so we're waiting for the rising edge. If it got into this block for a falling edge, so any transition of clock will cause that. It'll look at it and say, oops, I'm not going to do anything because it's a falling edge. And I'm looking for a rising edge, so if falls all the way down to this end of here. Now, if it is a rising edge, then we go down and we take a look at this other input, reset n, and if it's a low, then we initialize all the values. Else, we actually do something, in which case we go and we set like this LED to this bit value. And then we increment the counter. And so basically what will happen is every clock edge we fall, clock edge, check if it's a rising edge. So essentially every rising clock edge, when reset is high, we fall down to here, we increment the counter. When that counter counts, eventually we get way up in the upper bits, and it'll toggle, which will allow the LED to toggle. And essentially that is the brief intro to the Blinky example of a VHDL file. Now let's go back and see how our compile went. Looks not so bad. And I think there's one last thing after. Let's see, did we do so up arrow, sudo make install. Oh, so it did do it. Great. So let's do which GHDL. Let's see, GHDL. Does this work? So we gotta compile. And, unless we just installed GHDL. I'll take that. And so now we're ready to actually run these examples. So sudo, that's the GHDL window. Let's go back to this guy. Nice. So cat file ssh. So you can do this command here, which is going to analyze the blinky.vhdl file and also the test bench. And it looks like, for whatever reason, I left off the D. Okay, so now GHDL will analyze those two files. And created this work object. And then we do a GHDL-E for elaborate. And again, we tell it that we want the STD 2008 version. And TB is like the top test, the top module. It's kind of like the main program. And this one, I call it TB for Testbench. And that's like the top level of the hierarchy that wraps all the other stuff underneath it. And unknown. And you want to double dash. And there we go. So that compiled that. And then we do an ls. That kind of did some more. And then we're going to do a cat. Now we run the script. And now then we should be able to run this command here. TB. And hit enter. Oops. Nice. I could cut and paste. Okay. GHDL. Here it ran, and this is the test bench, like some of the code that I have, which we'll take a look at. It's printing out that this is for Blinky, and the LED changed from a 1 to a 0, and then it changed from a 0 to 1. It tells the time, like I've had 5246 nanoseconds, it changed from 1 to 0, and at 7806 nanoseconds, it changed from a 0 to a 1. And then the test bench goes and it measures the number of clocks from here to here. And in my example, I just wanted it to toggle every 256 clocks. And it did that. And let's see. And if it did do that, my test bench prints out a pass. If it didn't, it'd print out a fail. Eventually, if everything passed, then at the bottom it says test passed. If one of them failed, then it would say test failed. One of n measurements passed. And so that's essentially the test bench for it. So that takes you through a few of the stages. Let's see. I promised to do a quick GTKWaves intro. So if we do an ls here, right here is this VCD file that got created when we simulated it. And that's a value change dump file. And it maintains all of the transitions. Let's do a more on that file. And you can see in it, it defines, and you don't have to write any of this, but this is just for background. It's going in and it's defining some signal names. Like I have this signal name, a GPIO LED, and it gives it a symbol associated with it, or a group of characters, not anywhere readable whatsoever. And then later on, when things are transitioning, right here, you got that this symbol went to a 1 and this symbol went to a 0, which gets mapped up into this symbol here, maps into the clock, this parentheses. So you can see kind of like that this parentheses here is a 1, and it goes to a 0. And it also talks about like the times at which things are transitioning. So in that pound, and so this is like a time, and this is another time when things are transitioning. All right, so that's a VCD file. It's a commonly used opens file format for Verilog and VHDL simulators. It's also used for quite a few other things, modeling when you have many processes firing and you want to keep track of what's happening when. I've seen people end up using this file, and then you get to use something like GTK waves to see what actually is going on with all these multiple signals that are changing at, at, at the same time. So test right there, and GTK wave comes up. It's got the nice surfer guy here. Let's make this click on full screen, and then let's open up. Let's open up Blinky. Let's go down to here. You can select signal. So here is the hierarchy window. This is the signals in each level of hierarchy. This is the waveform viewer. And so you can go in and you can add a clock. So you select on it, you can drag it over, or you can append it, or you can double click on it. And right here, you're not seeing anything happening. This clock should be going very, very fast. And when you look at the time scale, it's in femtoseconds. I don't know how fast that is, but that's very fast. Much faster than we actually wanted to care about. But GTK waves starts out um, in maximum zoom, the zoom in, and we want to go maximum zoom out. And so, like, we got some zoom things in GTK waves, so we got to zoom out, zoom in, and this zoom fit, which I use to do a zoom full. So let's click on that. Boom. And now we get this solid bar here. And now if you click on there's a few ways to do this, but let's use the left mouse click. No, let me say that again. I'll use the right mouse click, click and hold, and drag, and let go. You can see you zoomed in. Let's do it again. The right mouse button, hold, drag, zoom in. And you got a nice clock going there. Now say you wanted to add this signal here. You can do, I think, control, and that'll select this guy here. Or you select this guy and you click on shift and do a left click. That'll select everything in there. So that's nice. And then let's go append that. And now you get all these signals going. So you can see on this clock, the counter's going. Um, the LED is high. We want to see the LED go transitioning. So let's do this. Click on the zoom fit again. And boom, now you can see this LED is many clocks. For many clocks, it's high. For many clocks, it's low. For many clocks, it's high. So that's pretty much what we want to see. And we can, again, right click, hold, drag. We can zoom in. Right click, drag, hold. Let's see. Right click, hold, drag, zoom in. And you can see these counters counting, where it goes 1FB, 1FE, 1FD, 1FE, 1F. Then it goes wraps to 0, 1, 2, 3, 4, 5. And these values are hex values. If you prefer to see it in decimal, you can left click on the signal name, right click, go to data format, slide to the formats, go down to decimal, and left click. And now you can see it goes 5, 5, 6, 7, 8, 9, 10, 11. So we're no longer dealing with hex values, we're decimal values. So that's kind of nice. So we can look at signals, we can zoom in, we can zoom out. You can with the middle scroll button, zoom left or right. If you click out here and you zoom up and down, let's see, let's not do that because we don't have enough signals. But you can zoom left or right. You can hold the shift key. It's still left or right. Hold the control key. Does a nice zoom in and out there. So let's see if we clicked on this. Zoom in, zoom out. It's not bad with a control and a scroll wheel. We can zoom in very nicely on that way. That's an alternative to right click, drag, let go. So two ways of zooming in and out. Signals transitioning. I think, what else do you ever want to see? I think that's really good. Let's minimize that. Let's do a quick hop back to the test bench. Let's see, so it's running. If you want to put it in the background, I could have started it with an ampersand. So I could have, well, I'll show you that in a moment. So if I do it, but I did not. So I just did GTKWave test VHD. I could have put an ampersand there and it would have started in the background, but I did not. So let's do a Control Z. That puts it in the background. Well, that suspends it. And then BG puts it into the background, which means it's still running. And now we've got this guy still running, but it's not hogging up our terminal. And do an ls. Let's see. So I could have started like that program with an ampersand, and that would have immediately put it in the background. Ls. Let's see, cat. A quick blast through the test bench. Let's not spend too much time because this video is getting pretty long. All right, so this is a test bench that I wrote. It's crap, but it's fine. It's a good starting point. Again, we start with all these libraries. IEEE lib is the most common library you'll almost always have, and you'll almost always use standard logic.all and numeric standard.all. If you want any text, put that guy in there. This adds like the finish command and a few other commands. So put all this almost always in there. There's a great debate about library work. Probably I shouldn't have it in here, but I do. I think you don't need it. Then it starts with an entity, and I call it Testbench. There are no ports to it because it's the very top level, and so like it's just a start entity and an end entity. And we have in the architecture we defined a bunch of signals that kind of keep track of stuff and help us pass fail. Again, we have the standard logics. We also have standard logic vector. We also have like an integer, which is a normal integer that you and I are all familiar with. Here we have a block that generates a clock. It's a process. So basically what happens is the process starts, it waits 5 nanoseconds. Then it goes in and it drives this clock signal to not clock signal. So it inverts it. Then it hits the process and it bounces back to the top. It does not have a sensitivity list, so it comes down and here it waits 5 nanoseconds. And then it does it again, inverts a 0 to a 1 or a 1 to 0. It just repeats that, generating a pulse every time. So in here, this is how we generate a clock, toggling every 5 nanoseconds, which means it pulses every 10 nanoseconds. And 10 nanoseconds is, you do the math, 100 megahertz. Which means it's toggling 100 million times per second. And here we're instantiating the blinking block. And so that's where I give it a U just to make that's the instance name. And then this is essentially the module name. Then we've got a generic map. Now also there's a way of doing things with the components. I tend not to do that because I came out of the Verilog world. Or actually I came out of the VHD world, then the Verilog world, and now I forgot how to do the VHDL world. But like I tend not to use these component notions. And I just do a worked up key. So I recommend it. But you do what you must. And then you got a generic map, which is saying this count width I'm passing in is like 9. So that gets you to like the higher level can set basically a constant inside of the block. And then we're mapping in, we have a port map where we map the internal clock signal to the external system clock at 100 megahertz and the internal reset end to system reset end and the LED to GPIO LED. Comma, comma, no comma. I always forget and I ended up having a comma here. Yeah, and then we blast through the test bench, which is just a process, which means it starts, it runs till the end, and it starts up again. And in this case, we have a finish at the bottom of it, so it'll never get to the end. And the finish causes the simulation to stop. And the report is kind of like a print statement, kind of old school Pythonic, where you do a string concatenation to combine stuff together. Also kind of like Pythonic of like, Python as an str. VHDL is more verbose and they have 2-string instead. So you can convert integers to strings or standard logic vectors to strings. And so that's just printing something out. Every print statement automatically has, every report statement also tells the time that it happened, and I think the block that it happened by default. Um, And then this wait until rising edge means that it just stays here until it sees a rising edge on this clock, which is generated by this clock generator. So this is a way of making it like advancing, like this guy advances time, and this guy follows along with the time. So we're waiting for every 10 nanoseconds, or in 10 nanoseconds, we see a rising edge. Then we drive this signal to low. You can see we have single quotes around it, similar to a character in other languages. And then we have a for loop, and it's similar to Python. And then for I in a range, and the range is 1 to 10, you do a loop. And so we have a loop instead of the colon. Um, and then we have, in this guy, we have the end loop instead of nothing in Python. So, but of this loop and then the end loop. And then we drive this guy to a 1, a logic 1, which is again in single quotes because it's a standard logic signal. Um, and then we have a for loop. If you wanted, you could put it all on one line. Um, so it does it for loops 10 times, waiting for 10 rising edges of the clock. And then we have another for loop. And then if you wanted to go from 0 to some value -1, you could put in 0, and this value -1, which is similar to Python. Not quite as clean as Python, but the concept of the rudimentary concept was there back in 1980 something. Um, and then in this case, I'm signing this guy like the value that's coming out of the blinky block to this secondary register. So now we have two values. We can compare them and see if there's an edge. And then if we wait for a rising edge of the clock, did the value of the previous clock cycle, is it different from the current clock cycle? And if they're different, then we fall in and we start doing some test measurements. So we want to see how much time elapsed. So we've got this ii, which is this loop count, which is kind of counting like clock cycles essentially, and the previous time that we captured that, and we get the delta, and if the delta equals 256, we report that it passed, else we report that it failed. We had a special case of a first time thing, so it's like a boolean that I set up so that like on the first measurement it's kind of squirrely because we didn't have a full duration. We had some other clocks like this 10 up here that messed it up. So we want to skip on the first guy. If it did fail though, but all the subsequent ones, we want to fall into this loop if it's not the first time. And if it failed, then we bump the fail count and report this. And then we keep bopping through. We do a little wait, another for wait, let some more time pass, and then we print out a final test pass, test failed. Then we hit the finish, which stops the simulation. We end the process, we end the architecture. That's it. Let's see if we can edit out that middle part.